So actually, last time we have stopped this page. If we know there are 2 points on the same plane figure, let's see this figure. If we know the velocity information of 1 point like A, so if we want to find the velocity information of point B, we have this method we call the pole method. Actually, in Chinese, we call that 基点法, right? So let's say actually this, I can write it again here. So we write at VB, it is absolute velocity equal pole's velocity, pole point VA plus VBA, right? So actually this is kind of we can compare from what we have learned theorem of velocity composition of a point. We have this absolute velocity equal a transport velocity plus relative velocity, right? But this time actually we are using the same, because at this equation we are talking about like moving point, right? Moving coordinate system and a stationary coordinate system. And here we use this expression to 2 points on the same plane figure its relationship between its velocity, right? So actually, we can think about that we have a MCS on this point A, right? And this MCS, it will move with this point A, but when this figure has some rotation component, this MCS will keep in this position and don't rotate with this plane figure. So the absolute velocity of point B can be divided into 2 independent components, right? So one component is the same velocity of pole point A, is VA. So it's more like this VE, The other component actually VBA, like we are sitting on this point A, we look at this point B, and we will find actually this point B has a rotation movement around point A. So this VBA actually will equal what? VBA is magnitude will equal omega AB, or omega of this figure times the length of the link line AB, LAB, right? So if we can find magnitudes of VBA, then we can find this magnitude of omega, and we can find its direction. So like from this figure, we can find, if we know first this omega with the CCW direction, then if we try to find its absolute velocity, so we will use this expression. So first, we'll draw this VA. So its direction and magnitude will totally equal to this VA, right? Then we are going to draw VBA. We know the direction of VBA will perpendicular to the link line of AB, but it can be this direction. It also can be this direction. So actually, we always I always told you guys to use this method. We can prolong this AB a little bit with this dashed line. Then we should, according to the direction of this omega, let this dashed line rotation along this direction of omega with 19 degrees, right? So you guys can find actually way along the direction of omega along the CCW direction, we find when this dashed line rotates 19 degrees, we get the true direction of VBA. And then this VBA is a vector and VA is another vector. Then these two vectors can constitute a parallelogram. and the diagonal position will be the absolute velocity of point B, that is VB, right? So actually, that's what we have learned last time, right? Today, we are going to talk about velocity projection method. Actually, it's very easily to understand. So you guys can find this. So if we have this link line AB and we prolong AB into this until here, maybe let's give let's see, it's H, right? Actually, we have a whole line ABH, right? So you guys can find, if we see this equation is a vector equation, right? We always use this method. We can define a positive direction of axis can 1, right? And then we can projection some vector equation onto that axis. So this time we are projecting this equation to AB. Actually, AB denotes its direction from A to B. It is the direction of C1, right? So when we do this projection, we will do from the left to the right. So the first we can find, if we try to project VB onto this line, that is the direction of AB, then we should know its direction, right? We should know its direction. So we can, let's see, this is alpha. No, let's see, this angle is alpha, and this angle is beta, right? So we can use this. So VB is magnitude times cosine alpha. You see, actually this guy is times cosine alpha is projection component will along the positive direction of this AB, so it's positive. Then we draw this equal sign, right? Then we should consider this VA, if let's say we know the intersect angle between the link line AB and direction of VA, then we can write as VA times cosine beta, right? Because this projection component is also along the positive direction of AB, then we should plus this component VBA, but we know actually vector VBA is perpendicular to this AB or this ABH. So its projection component will be what? Will be 0, right? So actually we can get this expression. It seems to this. So we call that theorem of velocity projection. In Chinese, we call that 速度投影定理. 速度 means velocity. 投影 projection. 速度投影 theorem, we Chinese call that 定理. Like some principle, right? So you can see actually because of this, because this VBA is direction always perpendicular to this link line AB. So when we do this projection, we will find this relationship. So next time when we try to use this so-called velocity projection method, if there are 2 points, let's say, maybe let's say M and N. If we know Vm is direction, and we also know Vn is direction, then if we can find its intersect angle here and intersect angle here, then we can always use like this. So this Vm, right? And this Vn. We can always use the same relationship like this. So we can write Vm is magnitude times cosine alpha equal Vn times cosine beta. But I think there one thing you guys should pay attention to is if you find like this, if you find when try to project this velocity onto this axis, if its direction projection component is opposite to this direction, then you should give a minus sign accordingly, right? So maybe you guys don't understand what I'm talking about. I will try to give you another example. Let's see. If we have a bar AB, right? That it is rigid body, and we know it will have a plane motion. Then if we know like VB like this, let's see, and let's see VA like this. I just show you how to consider this situation. Maybe not correct, right? But if this is alpha and this is beta, so when we do this projection, we should select a positive direction, which we can select it arbitrarily. It can be AB, it also can be BA, right? So if we think this is the direction from AB, so when you use this velocity projection method, we should write at VA cosine alpha, because it is projection component will along the positive direction of C1, right? And then equal, this time you will find VB times cosine beta actually is projection component will along the opposite direction of C1. So we should give minus VB cosine beta, right? So please pay attention to here. It's not very common. If that is the case, you should remember when you do this projection, you should always pay attention to its projection component. If it is the same direction of C1, then it's positive. If it is opposite to this direction, you should give it minus sign, right? So that's the theorem of velocity projection about. So we can use this sentence to repeat that. The velocity projections of any 2 points, right? Any 2 points in a figure on the line linking these 2 points are identical. This method for find the velocity of a point is called velocity projection method. So in some time when we are trying to solve some problem, we will find this method is very useful. It's very simple. It's very useful, right? Maybe we will find a kind of example. Then we are going to talk about another thing, that is instantaneous velocity center method. So do you guys still remember last time? Actually, last time we stopped after we finished this example. Do you guys still remember? You can all the math I write on this screen, but this point C is a very special point. So because this wheel is a pure rolling, right? We said that 纯滚动. Then this point C is a very special point. That is, its absolute velocity will always be 0. So actually, we call that in this time moment, any other points on this plane figure or on this rigid body will be treated as it rotate. It is rotating around this point C with the same angular velocity omega, right? So actually we have check 3 points like A, B, and D. You guys can find this right direction here and here. You can find actually absolute velocity V A, V B, and V D, all perpendicular to the link line from this point to the instantaneous point C, right? So we call this point is what we will learn today, instantaneous center, right? So this this instantaneous velocity center, we call that 顺心法。顺心法。So you guys can just look at this picture. So consider a plane figure like this ice. The velocity of point A is very special, like just to help you guys to understand this method. Let's say this VA on this plane figure has a horizontal direction and this magnitude. And we also know the the angular velocity of the figure is omega with CCW direction, right? And we take a line, actually, we just draw a line which is perpendicular to VA. You know, actually, we select a special line. Actually, this the specialty of this line is this line L prime. It is perpendicular to the direction of VA, right? Then we will use the theorem we have learned, right? So we can select a point arbitrarily from this special line L prime, right? Let's see, we just select a point P on this line L prime. So we will use this. So if I write it again, I can write as VP vector denotes its absolute velocity should equal VA plus VPA, right? And we know this VPA, its direction will always perpendicular to the link line between this point P and this point A, right? And its direction actually will be, we just need to use the direction of omega. So once again, we will prolong this AP a little bit. We got this part and we rotate it with 19 degree, but we shoot along the direction of omega. Then we can find the true direction of VPA. And this VA actually is the pole point VA. So you guys can find, actually, my network situation is not good enough. Can you guys still hear me? If there's something wrong, you can just tell me. I'll just send me some message, okay?
Okay, Nancy.
Okay,
Okay,
so
Nancy.
you guys will find actually here, because the specialty of this L prime, this VA and this VPA has opposite direction. So which is positive direction of horizontal line and which is another. So you guys can think, actually, when some condition is fulfilled, we will definitely find some point P, VP, it will equal VA plus VPA equal what? Equal 0. Can you guys think about that? Can you guys understand that? Because we always have, this is the vector equation. Actually, when we talk about the magnitude VP, so you can find, we do not draw this arrow again. We just talk about its magnitude. So we will always, like VA should minus VPA, which should equal omega times LPA. So if we select a special value of LPA and let this will equal 0, right? It's very easy to find, just like LPA, the length of P and A equal VA over omega, right? That's easy. So this figure and this concurrent tell me we can easily find a point that its absolute velocity will be what? Will be 0, right? So that is at any instant, why we call that instantaneous velocity. At any instant, there must exist a sole point. 有且仅有一个 you know, only one. So sole means only. There only one point whose velocity is 0, which is called the instantaneous velocity center of this figure at this instant. So let's see. Let's say this instantaneous point, just use an I to denote it is instantaneous point. So we can once again select this instantaneous point I as a pole point. So any other like Vm, it should equal Vi, right? Plus Vmi. But we know the instantaneous velocity center, its absolute velocity is 0. So this expression will be simplified into just Vm only equal Vmi, right? Which will equal omega times length mi. You see? This expression tells us when we find this instantaneous point, then all the other points on this same plane figure, we can just use omega times the length between this point you are selected to the instantaneous point I, right? If we know the length, we can very easily find the direction and the magnitude of its absolute velocity Vm. So this method, we call that instantaneous velocity center method. So then we will try to use, if we try to use this instantaneous velocity center, we should find a method to find the position of this instantaneous velocity center, right? If we can find that point, then any other point on this same figure is velocity, absolute velocity, direction, and magnitude will be very easily find. Just use omega times the length between these 2 points, right? So then we are going to talk about how to find this instantaneous velocity. So until now, you guys should know that at any instant, there will only have one point whose velocity, absolute velocity is 0. We call that the instantaneous velocity center, right? Then we are going to talk about how to find this point. So let's see. Then we are going to talk about the method to determine the instantaneous velocity center. So there have a different situation. We will talk about one by one, right? So the first is, you guys can just look at this picture. When the velocity VA of a point on the figure is known like this, then the angular velocity omega also know. So here in this figure, we will find actually this direction of omega is CW direction, clockwise, right? So if we know a point's absolute velocity VA and we know its omega, magnitude and direction, then the instantaneous velocity center point P can be determined. AP equal VA times omega. So I hope you guys can understand. So let's say, assume that we know the position of instantaneous point P is here. So we will know actually VA have to equal omega times length of PA, right? That's LPA. Here, AP means LAP, right? So we will find, because VA we know, omega we know, so that LPA will only equal VA over omega. So the only thing is, should that point P at this position or that position? Maybe here also another position which have the same length from this point to this point A. So how to select the correct position? Because at any time instant, only one point is its instantaneous velocity center, right? So that is the direction of omega, right? So let's say if you select P at here, and then you use the method, you prolong PA a little bit, and along the direction of omega rotate 19 degrees, then you find this VA is not the correct direction of the original direction of VA. So that is paradox. 矛盾, not correct. So it should be VA. So that means we only need to draw a perpendicular aid line, aid, 辅助线, right? Aid line. Then we'll, according to the direction of omega, find a appropriate point position P, and should let that use this P and omega times AP can determine the correct magnitude and the direction of VA, right? So this is the first situation. So we have to draw eighth line, which is perpendicular to the direction of VA. This is the first situation. The second is, so when a plane figure rolls along a fixed surface, so this surface can be a plane or can be a curved space like this. So I can draw another example for you guys. That's the same conclusion. So this will also can just rolls along a fixed ground, right? It's just a plain ground. So these two examples are identical. Without slipping, that is the pure rolling. We have talked about this condition. Actually, you can think about it is a terminology, 纯滚动, right? Pure rolling, 纯滚动. So that means if this condition is fulfilled at the contact point between this plane figure and this fixed frame, there will have no relative between these two things contact point. So in any time this contact point repeats, absolute velocity will always be zero. So that means because this is a plane figure at any instant, time instant, it only can have one instantaneous velocity center. Then this point, it is the instantaneous velocity center. So it's very complicated to say these three English words, but in Chinese we just use two Chinese characters, 顺心, right? So that means a few Chinese words can deliver more information compared to the English word, right? So we just call that 顺心, right? But if we express that in English, we have to see the instantaneous velocity center, right? So this is the case. Please, you guys pay attention to here. So I will repeat again. When a plane figure rolls along a fixed surface without slipping, the contact point P between the figure and the fixed surface will be the instantaneous velocity center, right? So it's very easy to find that. So then if we know that this P is the instantaneous velocity center, then any other arbitrary selected point like here A, we just need to link AP, right? Then we can find its magnitude will equal omega times LAP, right? But this time we don't know its magnitude and direction of omega. But you guys can think if we have a wheel rolls along the fixed ground, in many cases, we know the center, the geometrical center will know its velocity like this with 0, maybe also including its absolute acceleration a0. So we know the contact point C is instantaneous velocity center. So we will find actually V0 also equal omega times r. Let's see, this r is the radius of this wheel. Then we can immediately find omega will along this direction because we know the direction of V0 and its magnitude will equal what? Omega will equal V0 over r. See, that's a very helpful use of this instantaneous velocity center, right? So maybe we will use this again through some examples. So here we are talking about two situations and tell us how to determine the instantaneous velocity center, right? I think that the two special situation for some generalized situation, actually we only need to draw some added line, right? So let's see here. When the direction of the velocity VA and VB, let's say this is another plane figure, and we know any 2 points A and B, that means we know its velocity, VA's direction, VB's direction, also the magnitudes of VA and VB. So because if we know its instantaneous velocity center is in some position, let's see, maybe here, right? It must be fulfill these two conditions. So VA should equal omega times LPA, right? And VB should equal omega times LPB, right? So here we know VA, we know VB, but we don't know omega and LPA, omega and LPB. But there one condition is we only have one instantaneous velocity center. So we just need to draw a two-added line. So first we draw a line which is perpendicular to VA, right? Then we draw another line which is perpendicular to VB. So you guys can think about that. These two lines will intersect at some position. Actually, this intersect point is the instantaneous velocity center we are looking for, right? So let's see here. And VA is not parallel to VB. So you can hear VA, direction VA and direction VB not parallel one to each other. Then we should draw lines from A and B perpendicular to VA and VB respectively. And the cross point P, I said we will have an intersect point, right? The cross point P of these two lines will be the instantaneous velocity center. It's easy, right? It's easy. So, but if there are some special cases we are encountered, we should consider that. So you guys look at these two situations. So if VA and VB, the two directions is perpendicular to each other, it also can subdivided into two categories. One is VA and VB have the same direction. Another is, although they are perpendicular to each other, but the direction of VA and VB is opposite. Then we can use some method accordingly to find the position of instantaneous velocity center. So this you guys can find almost all the situation, including 1, 2, 3, and 4. All we should to do is draw the perpendicular line, right? So we can think about we draw line first, we draw line second. So this time we must find some position to let that VA equal omega times LPA and VB equal omega times LPB and should be consistent. should 一致. There are no paradox, right? So you guys can find we only need to use these two expressions, then we can find the position of P. In the second category, because VA and VB have different or opposite direction, then we will know that the position of P will in the internal position between the link line A and B, right? And here it outside the link line AB, right? So I think you guys can easily figure out why it is true, right? I think it's not difficult. There also another case you guys should know. So this, this is the two case. So there also have this situation, The velocity of 2 points A, B, have same direction. VB and VA have same direction, but they are not perpendicular to line AB, So if we draw the 8 line, this here and this here, you will find actually this guy will parallel to this guy. So we will never find a cross point, right? Or we can see that the distance of that cross point to B and A will be indefinite, 无穷远, right? Indefinite. So this time we have a new concept. We call that instantaneous translation. That means only in this time moment, we have omega equals 0. It's more like at this time and only in this time moment, this plane figure has translational moment. So then VA will equal VB, have the same magnitude and same direction, but you should know acceleration is not the case. This is not AA not equal AB, right? So this is very important. You should pay attention to. So in this case, the instantaneous velocity center is indefinitely far away, right? If far enough, then the distance between A and B have almost zero influence to the position of instantaneous velocity center. So we will see its angular velocity omega equals 0. Why equals 0? Because if we see VA to the equal omega times LPA, but this guy equal indefinitely bigger, right? Because it's bigger enough, then omega will equal VA over this. Omega will equal VB over this. So it will equal 0. So we call that only in this time moment, it has an instantaneous translation. But their acceleration are not identical. You guys, please pay attention to this. And maybe we will also find this situation. So although they have a common 8 line, which is perpendicular to VA and VB, but VA is magnitude equal VB. So this time we only also have this conclusion. It called instantaneous translation, but their accelerations are not identical. That means AA not equal AB. right? So that's some situation we should consider about the instantaneous velocity center, right? Uh, let's see. Let's see example. We will use what we have learned today. Uh, so let me erase what. Let me erase this, right? So you guys can follow me, look at this example. Let me read it first. So you guys just look at this figure is enough. So at the instant of time shown in this figure, the rod BC, the red link BC, in the crank rod mechanism, I have told you guys, this is 曲柄 crank rod actually also should have a slider. So crank rod slider mechanism, slider. We call that 曲柄滑块机构。曲柄滑块 mechanism means 机构. You can also think about it, the body system. All the body are rigid body, right? In crank rod slider mechanism has instantaneous translation. 瞬时平移. This is another terminology. Instantaneous translation, we call that 瞬时平移. 瞬时平移. You know why? Why this is correct? Because, because this horizontal slot, which is fixed, so because it's guidance, this slider, yellow slider only can move along horizontal line. So that means we see its direction will along this horizontal line. And this position AB is upward. Because this point B also is the rigid body AB's point. It has a rotation around the fixed point A. Use this direction of omega, right? So I think actually there's something wrong here. We can maybe you get real confusing that actually this is not correct. I can just change that omega actually is CW direction. Then this B will totally along this direction. Why? We can prolong AB, use the dashed line, and along the direction of omega, I have corrected it into CW direction. Then with 19-degree, we will find VB. And because of this guidance of this VC, its velocity will along this horizontal line. Then if we try to find its instantaneous velocity center of this bar BC, we have to draw two lines. One is this line, which is perpendicular to this VB. Another vertical line will perpendicular to this VC. So you guys will find actually this 8 line and this 8 line is parallel to each other. These two lines will have no cross point, right? So that means it has instantaneous translation, 瞬时平移. Then we will have the conclusion in VB, magnitude equal VC, right? So that's why VC also should along this direction. So VB and VC, and this time omega BC will equal 0 because it has instantaneous translation, right? Let's continue. The angular velocity of BC, omega BC equals 0. Why? That's the reason, because it has instantaneous translation. The velocities of all points in BC are identical, but their accelerations are not, right? So let's say if omega is uniform, uniform means it is a constant, right? Constant. And omega dot will equal 0. That means this bar AB will have no angular acceleration. Then this AB, maybe you guys cannot remember this anymore. This AB will only have one component along normal line direction because actually, maybe I will review that. If we know a point that's around A with the circular rotation, that this is B, along some omega, actually is without acceleration will have AT, right? Along tau direction. Also have another is AN along normal line direction. And this AT should equal angular acceleration alpha times what? Times R. Actually is from A to B, R. But here, our omega is uniform. So alpha is 0. So this component will be 0. That means it only have ABN. And that is AN will equal, always equal V squared over rho, which is omega squared times R. See? So we have omega squared times AB. AB means length of AB, right? So we will know is AB, that means B is acceleration AB will along the vertical direction, downward direction. But the slider B only can move along horizontal line. So anyway, its acceleration AC will always along horizontal line. See, that's why AB cannot equal AC, right? So we have AB not equal to AC, right? That's why. So you guys should know instantaneous translation is big different from translation, right? It is only at this time moment. But for translation, we always have its main characteristic is 2 points on the body who have a translation is VA always equal VB and AA always equal AB. So that's all for the first class today. So you guys, let's have a short break. We will restart our class today at 11:10. So please, all you guys have a rest. I'll see you then.
OK，老师。
好的，老
OK，
师。
好的。 Okay, everyone, let's continue. We have finished this page. Actually, the result is if we know some rigid body on a given mechanism, it has instantaneous translation. We should know at this time moment is omega. That means its angular velocity will equal 0. Any 2 points will have the same velocity, include direction and magnitude. But any 2 points is their accelerations are not identical. That is very, very important. Actually, we have give an example from this picture, right? Actually, the direction of B and direction of C, these 2 points acceleration cannot be equal, right? This is vertical and this is horizontal, cannot be identical, right? So this is very important. You guys should, please, you guys should pay attention to that. And when we know how to find the position of instantaneous velocity center, then we can use this to help our problem to be tackled, right? So any point, we can arbitrarily select a point on the plane figure. If we know P is the instantaneous velocity center at this time moment, at another time moment, we also have another instantaneous velocity center, which will definitely be in a different position, right? So let's see the analysis. The position of the instantaneous velocity center. So it's very complicated to read this. Maybe we can just use like we use MP to denote moving points. We use MCS to denote moving coordinate system. So maybe we can use IVC to mean instantaneous velocity center, right? It's very easy to read it again and again. So the position of the IVC is not fixed at all time. The position of the IVC is not fixed at all time. It changes instantly with time. So let's see, actually P equal PT, that means its position will be changed at different time moments and exists uniquely at any instant time. So guys can think about that. We can draw a trajectory line of the out position of this IVC, right? Only the velocity at the instantaneous velocity center is 0, but its acceleration is not certainly 0. It may be 0, maybe not 0, right? This differs from the rotation about a fixed axis. Maybe you guys don't know what these paragraphs are talking about. Actually, it tells us if we know a point P on the plane figure is this time moment IVC, then it means Vp is absolute velocity Vp will equal 0, but its absolute acceleration AP in many cases not 0, right? So it tells us, but its acceleration is not certainly 0, 不一定是0, right? This differs from the rotation about a fixed axis. If we say we have a bar like OA, and it rotates with omega and angular acceleration alpha around point, let's see this A, around point O. So in different time, all the time, this point O will also have two VO will equal 0, AO will always equal 0. Why? Because this O always fixed, right? And here we are talking about IVC. Actually, it is not fixed, right? It changes instantly with time. So that's the big difference between this IVC and from the rotation center about the fixed axis, right? And when a rigid body is in instantaneous translation, 瞬时平移, although the velocities at all points in it are identical, but their accelerations are not necessarily identical, right? This is different from the translatory motion. Maybe this is wrong word, but translational, I think translational motion, right? Translational motion. So that's all the instantaneous velocity center about. We have one is how to find the position of P, and another is the difference from this P, right? It's very important. We should pay attention to that. Here we have example. Let's see. We have a crank rod mechanism, right? And OA equal AB equal L. And the crank OA rotates with the uniform omega. This is CCW direction. Find when phi equal 45 degree, the velocity of piston B and the angular velocity of rod AB. So I'd like to give you guys maybe 5 minutes to think about how to find this result. After 5 minutes, maybe 11:25. Can you guys give me an answer, and we will do it together? Try to find if you guys can give me a correct answer, right? So start. You guys can think about by yourself. After about 5 minutes, I will learn that together. Okay?
Okay.
Okay. Try it. Try it. Start. Okay, can you guys find the answer? Anyone tell me the velocity of piston B? Okay, that's fine. Let us do this again together, right? So actually, you guys can find we have from the condition it tell us, right? We know OA equals OB equals L, right? And actually, we have crank OA rotates with the uniform omega, right? So you can find actually we know the magnitude of VA equal omega times L, and its direction will perpendicular to OA, right? Why it should along this direction? Actually, you know, I tell you guess this all the time. So you can first prolong OA a little bit, then you should, according to the direction of omega, rotate this dashed line with 90 degree. Then, because of the direction of omega, we will find VA will be this. If our omega is CW direction, then you can find our dashed line will along this direction, right? And since it tells us this is 45, right? 45. And because this OA equals AB, then this angle have to be 45 again. Then this OA will perpendicular to AB, right? That's all we have the conditions, and we have the magnitude and direction of VA. Then we are going to use the method we have learned to find the question. The first is the velocity of piston B, that is we try to find VB, and the angular velocity of rod AB, that is omega AB. So actually we can use different methods to find the answer. Let's do it one by one. Maybe I will change another color of my pen. So please, you guys, just please, you guys follow me. Actually, you guys can think about when OA rotate along this direction. Actually, this point A will all be along a fixed circular trajectory, right? And the force from OA to piston will along the direction of AB. So I think it from our life experience, when A move along this direction, the most this VB, because this fixed slot will get the piston only can move along horizontal line. So I think the most correct direction of VB will along this direction. Can you guys agree this? Can you guys think about this? So because, right, it's very easily to understand, right? So VB should along this direction. Then the first method we can use is, so we have different methods to find the magnitude of VB. So first is we have learned projection method, right? Projection method. So you can find actually we have the link line AB, and we know VB in most will along this direction, so it intersect angle with this AB the 45, and VA actually is along the BA direction. So we can think about we just projection VB and VA onto BA direction. So we have from this projection method we have VB is the magnitude times cosine 45, right? Just equal VA and its magnitude just omega L. So it's very easy to find the magnitudes of VB equal omega L divide, right? Divide over cosine 45. That is, we should times this. And the final result will be square root 2 times omega L. So this is the first method, right? We have get the magnitude of VB successfully. So what is the second method? Actually, because this AB have what? It tells us this AB have a plane motion, and A and this rod AB have a plane motion, and AB are 2 points on this rigid body. So because all the information on point A is known, right? So we will just select A as the pole point. So if we try to find VB, we will have this expression. VB will equal VA plus VBA, right? Then we can draw our vector on point B. I have to change another color again. So you guys can find when we write this expression here, we should draw the three vectors on the point B, which we are going to find is velocity, right? So that is its absolute velocity VB we draw here. Then we should draw VA. At this special position, then our VA will just need to along this. See? It's hard, a little bit hard to draw this. No? So this is VA. Then we should draw VBA. You know, VBA, its direction should be perpendicular to the link line AB. So maybe this direction, maybe this direction, but we know it must be this direction, VBA. Why? Because VB equals this vector plus this vector. We should always keep this guy in the diagonal position of that parallelogram, which is constituted by VA and VBA, right? We have seen this all the time. So we should always remember that, you know? So you can find actually this VBA will perpendicular to this AB. So if this angle is 45, then this angle also is 45. Right? So you find actually VBA perpendicular to VA. So we will have we have this triangle. So actually this is VBA. So here will be 90 degrees. So you guys can find actually we also have at this rectangle triangle, our VB is here, right? So we can find VB times cosine 45 will equal VA. You see? We have the same relationship, right? So we can find the same result. So VB will equal square root 2 omega L. And from this method, we also can find, it's very easy to find VBA because this is 45, this is 45. So we can find VBA will equal VA equal omega L. Can you guys understand this? Can you?
Yes.
It's easy, right? It's easy.
Mm.
And we also know actually omega B, VBA also should equal omega AB times LAB. So you will find that's great. It because LAB is L, so you find actually the second answer of the angular velocity of rod AB actually is omega AB just equals omega, right? Just equal omega. Because omega L is what we have from this relationship, because we have this rectangle triangle, this 45, this 45. So VA will equal VBA. And VBA also should equal omega AB times LAB. And once again, we should have the direction of omega AB. So we can think about we are sitting on point A. We look at point B. It will have a rotation movement around A. Since VBA along this direction, then we will have this conclusion. Omega VAB will along this CW direction, right? Which is opposite from the direction of this OA. So although it have the same magnitude, but the direction of omega and omega AB is different, right? So that's the two method we find the velocity VB. Actually, at second method, we also find the angular velocity of rod AB, right? I will erase all the things I have right on the screen and give you another method. No? So actually, we also have another method to find omega AB, right? So let me draw VB here again. So this is VB. And this time we are going to use IVC. Do you guys still remember this? Instantaneous velocity center, right? So since AB are 2 points on the rigid body AB who has a plane motion. And since we know this 2-point AB is direction of velocity, so we just need to draw two lines, right? So this VA actually, this OA is perpendicular to VA, so we only need to prolong this line to some distance, right? Another is we should cross B, draw a vertical line, which is perpendicular to direction of VB, right? So you guys can find it difficult for me to draw this. I hope it will help you guys understand. So actually it will be 90 degrees, right? Let's see, this is our instantaneous velocity center I. So if here is 90 degrees, here just the prolongation of this OA, so here will be 90 degrees, right? And here this 8 line will perpendicular to here. If here is 45, right? And here will 45. And the total angle of this is 90 degrees, so also 45. This is also 45. So from the geometrical, if AB equals L, then this AI its length will be L, right? Right? And from all this, we can find our two answers, you know? Let me change into right again. So you guess if this I is IVC we find at this time moment, then VE, although we know it equal omega L from the information of this OA, it also should equal what? Omega AB times L IA, right? The distance from this point to the IVC, and should equal omega L. Actually, we have find LIA actually equal L. So you guys can find, we easily find omega AB should equal what? You know, because this relationship, this is L, so we can eliminate this one and this one, then omega AB have to equal omega.
Omega, yeah.
Right?
Yes.
Okay. Then we should try to find the direction of omega AB. You see, you can think about you are sitting on point I. You look at point A. Since it have a direction of this VA, that means from here it must have what? Have this direction. Right? You also can think about you prolong IA a little bit, and you should rotate around some direction less VA like this. So you have to rotate this dashed line with CW direction. So omega have to be CW direction, right? And then if you guys can understand this magnitude, you also can understand this direction. Then you can find here. Actually, VB should equal omega AB times LIB, right? So here is another rectangle triangle. So here's L. So this length will be square root second L, right? So you will find, we just find VB will equal omega AB equal omega LIB equal square root 2L. See? Also the same result. So until then, can you guys totally understand what I'm talking about?
Yeah, 老师。
Okay.
Yeah,老师。
Okay, that's great. Actually, that's this example. So maybe I will show you guys the answer of this slide. So the first composition method, consider AB and take A as pole. So we have VA equal omega L. Its direction is shown in these figures. So actually, I'm repeating the process how to use the composition method. So first we give VB, then we give the pole velocity VA here. And we should make sure VB on the diagonal position of this parallelogram. Then VBA have to along this direction. Right? Then we can find VB equals this. And omega AB equal omega and along CW direction. Right? That's the final result. I have shown you guys before. Let's see. The second method is velocity projection method. Actually, we have talked about before. So consider AB, VA equal omega L along this direction. And the direction is perpendicular to OA and VB is along VBO. Right? And maybe I will show you guys another thing. So actually, I think all this you guys will totally understand. And actually, maybe some students maybe have a question. Maybe it will have a question. Hi, teacher. Maybe I don't have many life experience. Although A along this direction, maybe I will wrongly think about that. Maybe VB along the opposite direction, right? It happens, right? It happens. Then let's see if some student from you, because you're initial learner of this course, maybe you don't have enough life experience to give the correct direction of VB. I'll show you guys, actually, that's fine. Don't worry about that. If this is 45, so this is 45, right? And this is 45. You just know because you think about VB maybe should along this direction. Then when we use this velocity projection method, we should make sure which direction we are going to project. So let's say consider AB. So maybe we project, you can arbitrarily select a direction, maybe AB direction, right, from A to B, also maybe BA direction. Our direction is fine. You should select one. Let's see. We just use this projection method along BA direction. Okay, along BA direction. So you will find the first, if we think about VB should along this direction, then you will find VB times cosine 45. So this projection component will opposite to the direction we select BA, right? Because BA is from B to A, but our projection component actually along the direction of AB. So we have given minus sign. So I think I have mentioned this before, right? And equal VA cosine 0. Because this VA is projection component actually along the direction of BA. So you will find your final result VB just equal minus, right? Square root second omega L. So the difference is if you think or you assume VB should along this direction, then your result will have extra minus sign. That means your assumption is not correct. The correct direction of VB should along the opposite direction of your assumption. But that's okay. That's also 100% correct. Can you guys understand me? Can you guys understand me?
Yes, Lotion.
VB can along this direction, can also along this direction, only if it's along the horizontal line is fine, right? So you just need use the correct projection method is enough. So maybe some guy has positive sign, maybe some guy has negative sign because its assumption of direction of VB may be different, right? So that's what I want to tell you guys. We should pay attention to this projection method. And the third method is instantaneous, right? Instantaneous velocity center method. You know, so we consider AB since the direction of VA and VB. Once again, you also can think about VB maybe along this direction. This direction also is horizontal direction. So it will not change the cross point P here, right? So we will find here AB equals L, then PA equals L, PB equals square root 2L. Then we have the same result. So you guys can review this typical example, and actually it covers all the methods we have learned today and the last time, right? It's very typical. You guys can try to compare these three methods. It's very helpful to help you guys to totally grasp all the knowledge point we have learned. Let's see, continue to talk about acceleration of a point in the plane figure, instantaneous center of zero acceleration. Actually, I will not cover this because I don't think we have learned this. Actually, when I teach my Chinese students, we don't talk about instantaneous center of zero acceleration. So we will not cover this topic. We just talk about acceleration of a point in the plane figure. Because we have finished talk about velocity of a point in the plane figure. Let's say if pole point A, another point B, we always have VB equal VA plus VBA, right? And we talk about instantaneous velocity center, right? We also talk about projection method. So when we talk about acceleration, it also have composition method, and it's very easy to understand because it's more like what we have used VA equal VE plus VR, right? That's from chapter 8. So actually, you guys can find we just compare to this and we change velocity into acceleration A, we will have our point B with AB, right? Equal pole points is acceleration AA plus ABA, right? And just need to change it that maybe because maybe ABA will have two components. One is along tangential direction, which will equal alpha AB times LAB. Another is along nominal line component, which will equal omega AB squared times LAB. Actually, that's all. That's all. So you guys can just look this picture. We have a plane figure as here. Assume that we know the direction of AA here. We know the direction of, actually, we always use this epsilon to denote its angular acceleration. We also use alpha, right? So epsilon here, omega here, then we are talking about absolute acceleration of point B. So you guys can find actually the AB will equal AA plus ABA maybe tau plus ABA n, right? So when we are sitting on point A, we just find this point B will rotate around the point A. Maybe it will have tangent line direction ABA tau and normal line direction ABAN, right? That means our ABA can be divided into two components. One is ABA tau, another is ABAN, right? So actually AB can be divided into three components, AA, ABA tau, and ABAN, right? Actually, the whole paragraph are telling us this. So if I use this, maybe it's clean for you guys to understand. So at an instant of time, the acceleration AA of a point A in the figure S, omega and epsilon are given, unknown, right? Find the acceleration of any point B in the figure. So we take A as the pole. Pole means at basic point, right? And fix the moving reference system, actually MCS. Take B as the moving point, right? So it's more like we are using the composition theorem, what we have learned from chapter 8. The motion of point B can be decomposed into a relative motion, which is circular rotation, right? And another transportation, which is translation, just with the pole, right? So we have this result. So employing the theorem of acceleration composition. So it's more like AA equal transport with acceleration AE and the relative acceleration AR. So do you guys still remember actually AR maybe also plus AC, which is 柯里奥利柯氏加速度, right? We have AC equal 2 omega times VR. But the good news is we don't need to consider this case anymore because our MCS will always have translational movement, right? Will always have translational movement. So that means acceleration of a point in the plane figure is very easy, because we do not need to consider 科里奥利 acceleration, 科氏加速度, right? I think this is it. If I clean what I write on screen, you will find this is our final result, right? This is our final result. And you guys should, maybe I should repeat that ABA tau or T is magnitude will equal alpha AB. Here we just use epsilon AB, right? Times LAB. And this ABAT N will equal omega AB squared. So we can use the velocity theorem. We just finished a typical example. We can use 3 methods to find omega AB, right? And times LAB. So you guys can look at this figure again. You can think about that. We just using all the known information, AA, epsilon, and omega. We try to draw this AB. Let me change the color and draw it again. So since we know this relationship is correct, so first we can draw AA totally according to the pole direction AA. So we draw AA here, right? We draw AA here. And since we know epsilon and omega, so we should draw ABA, but we can just draw it 2 components. One is ABA tau. It should equal epsilon AB times LAB. That means its direction will perpendicular to this link line AB. And once again, you guys can think about U prolong this AB a little bit. You have added a dashed line. Then along the direction of epsilon, because we are talking about to make sure the direction of acceleration. So we use the direction of epsilon, and then along its direction, rotate this added dashed line with 90 degree. Then you will find actually you ABA tau along this direction, right? Is this. And another component, ABAN, it's easy to have its direction because it's always from this point B, point to your pole point A, right? You don't have other choice. You always have to point from B to A, and its magnitude will equal omega AB, just here omega squared times LAB. See, I think that's all for this section, you know. Actually, you guys find actually this whole section is knowledge point I have finished, and it's time for us to terminate today's class. Maybe next time we'll talk about 1 or 2 examples, and then we are going to move to the third part of this course, to the chapter 10. Right? Let's see if we have homework today. I think that's all for today's class. Let me find the homework for you guys to do. So this is our today's homework. I hope you guys can finish this. And if you have some example, you can talk to me. We will do this together next time, right? This is our today's homework. Let me read it. A 4-bar linkage. So here AB rotates here. determine the velocity of point C and the angular velocity of DC, right? If you try, you guys can find the answer by yourself. Next time we will do this together, right? So
好的，老师，
that's all for today. 那我们今天就到这里吧，再见，同学们，
再见，
再
老
见
师。
再见，
OK，
拜拜
拜拜。
，Thank you，拜拜。Have a good day to you，侯云，Thank you，拜拜，
拜拜，老师。
拜拜，
OK，老师。
拜拜。